Alright, so we're continuing our cases here. Case 2 we're going to look at is the case where we have complex eigenvalues. Lambda equals alpha plus beta I with a corresponding eigenvector that's complex. Right, but our solutions are not complex. And so the question always comes up, well, how do I figure out, in the xy plane what I've got? So one thing to notice is that in this case, you're going to have the e to the alpha t come out as the real part in both the real and the imaginary part. And so we can say like e to the alpha t times our complex vector. It's going to be hard to note. I just want to mainly look at this because this alpha here, if that's a positive number, what's going to happen to your solution? That means the exponential function is going to blow up, right? If alpha is bigger than 0, your x of t is going to go to infinity in a plus or minus way. And then if alpha is less than 0, your x of t is going to go towards 0. And then the last case might be alpha equals 0. And in that case, we actually have a special case. The solutions are actually going to be periodic and cyclic. So it's going to look like your solutions are going to look like ellipses in the xy plane. Okay, and so we can kind of separate the cases then, the complex cases, based on the real part of our complex number. Okay, so let's take a look at an example maybe. Something like the matrix 1 minus 4, 4 minus 7. Okay, now I'll just go ahead and write down the lambdas. Those are going to be minus 3 plus or minus I. And so what's going to happen then? Are the solutions to this going to go away from the origin or towards the origin? Yeah, they're going to go towards the origin because this minus 3 is going to be interpreted to be an e to the minus 3 in your solution. And then you're going to have some stuff in here. And so what happens in here is you're actually going to have a spiral. And this is telling you that the spiral is going towards the origin. Okay, so this is going to be a spiral towards the origin. Now the question is it clockwise or counterclockwise? And so there is a way to figure that out. And the way to figure that out is to see what this direction field does, because we have x prime equals ax, right? So how about if I put in an x, like x equals 1, 0, and see what my direction is. So if I put in my 1 minus 4, 4 minus 7, and I apply that to the vector 1, 0, I get the vector 1, 4. Okay, so that means that the direction of travel from this point is going to be to the direction 2, 1, 4, which is over here. And so, do you see where we're going? We're heading in that direction. So therefore, the direction of our spiral is going to be counterclockwise, right? Counterclockwise. And so the spiral will look something like this. So you could just sketch it out this way. It's a spiral towards the origin. And in fact, how tight this spiral is depends on how big this number is. In this case, we just have one I, so it's not really going to be spinning this tight, but just for the sake of clarity, we'll draw it that tight. Okay. So similarly, if alpha is, if we had something like lambda equals positive 3 plus I, right, then you would have the vector, or the spin would be going away from the origin. Whichever way, it might be clockwise still or counterclockwise, we'd have to tell. But in this case, right, this is a spiral away from the origin because of the positive 3 there. Okay, and then if lambda was just equal to plus or minus I, you would just have a center. And then to determine the spin, we would do the same thing we did over here. You'd need to see the matrix in order to determine which direction the spin was going. Okay, and so let's do one more example. And in fact, we'll take a look at the online plotter as well. So one more example. If we have the matrix 1, 2, minus 5, minus 1, and we're told that the lambdas, we could compute the lambdas, but since we're here, let's go plus or minus 3i. So we know that it's a center. The origin is a center. Okay, which direction is the spin? So to find the direction, we could apply 1, 0 to our direction field to see where the direction is, and that would be 1 minus 5, I believe. And so if you're in your xy plane here, and you're starting at the point 1, 0, right, you're ending at 1, negative 5, and so where is that traveling? That's right, that's traveling clockwise. So we have a clockwise spin on our center. Okay, and so you might just draw the center. It may look like a circle or it might look like an ellipse. It's hard to tell without a little bit more information, but just a general picture, just a sketch is fine when you're doing it by hand. Now I've got the online plotter set up here so we can see it. And in this case you can see what's happening here, right? This is our matrix that I've put in. And then here you see their solutions. And so you can see that the direction of travel is the direction we were talking about. So you'll notice here, oh, what's happening here? Why isn't that a center? That looks like a spiral. What's going on there? Well, over off to the side here, you might see that we're plotting the numerical solution curves using Euler's method. Euler's method? That's not very good. Let's see if we've got some other methods. How about improved Euler or Runge-Kutta? Let's do Runge-Kutta. And now let's go ahead and see what happens when we plot some of these curves. There we go. Now you see what's happening. We actually do have a center now. So the Runge-Kutta method gave us a lot more accurate solution. Notice that when we were using Euler, it looked like we might even have a spiral instead of a center. So you do have to be kind of careful here. How about improved Euler? Does that give us a center? Oh, that does give us a center. Oh, good. So we didn't actually need to go to fourth order, but of course sometimes it's nice to just check the fourth order. Very good. And so now you see how to use the plotter here. You can also do like one differential equation. You can do a system of differential equations. We're not going to do polar coordinates, but you could do polar coordinates if you wanted to. Okay, so I would encourage you to try this out. It's a nice online plotter. It's going to be linked from today's lectures, so you can try it out yourself. Good. There is one more case that I was just going to mention. So this was case 2, right? Case 2 with complex numbers. Case 3 is when the lambdas are equal to each other. This can get complicated. And you can see, we skip this in the general case. Do you remember what we did in the 2 by 2 case? We said that our solution is e to the lambda t times, we didn't have arbitrary constants, that was the change, but we did have x0 plus t times the vector w. Do you remember how we got the vector w? A minus lambda I times x0 is equal to w. Okay? And so that was the case where we had the one eigenvector, or one eigenvalue. We're not going to draw these pictures. We might use it in the computer, but we won't draw these by hand. Okay, because they're hard to check. And you might be saying to yourself, wow, there's a lot of different cases here. How am I ever going to keep these straight? Well, there's a nice way of keeping them straight. And the technique we'll use, or the diagram we'll use, to keep these straight is something called the Poincare diagram. It's going to keep all these cases straight for us. And so the next video will be all about the Poincare diagram.